Howdy. So we're ready. Fun Chem 2, Chapter 13. So it's been a while, since almost 2 weeks since class. So we did some of this in class. I want to refresh our memory on some of the naming. I want to get into some of the new stuff, but let's go ahead and just start at the beginning for Chapter 13. So aldehydes and ketones. Uh, so um, not too difficult. So we want to learn how to name them. Keep in mind we're going to do IUPAC and common name. We'll also be working on ketones, aldehydes, ketones, oxidations, reductions. So we'll start with the review of our carbonyl groups. So we've got our aldehydes, ketones, carboxylic acids, esters, amides. We've covered all of these. So we're focused on aldehydes and ketones. So let's get a quick down look at this. So here's my little puppy dog. So carbonyl, carbon to an oxygen. So this is an aldehyde. We can tell because it's got hydrogen next to the carbonyl. So it's always at the end, we can see, because there's no other place for this to be. So that's going to come in on the naming. Carbon-oxygen double bond, very polar. The oxygen is negative. The carbon will be slightly positive, and so this greatly affects the chemistry. We also notice, unlike alcohols, there's no hydrogen on the oxygen itself, so there's no hydrogen bonding. If I pick up a ketone, we can see it's in the middle. So carbon, carbonyl, carbon, that's our pattern. So we're looking for, again, very polar bond, but no hydrogen bonding. So hang on. So switching over here. So when we're looking at these properties, and lack of hydrogen bonding greatly determines it. We can also see it's 120 degrees, so in between here, it's roughly going to be flat when it sits, but notice it also follows our general zigzag pattern, so we can still draw it just the same zigzag as we normally would. So carbonyl, not too hard. So properties on it, it's going to be a little more water soluble than alkanes, but not near as much as alcohols. Okay. So let's just switch on down here. So start off by naming aldehydes. Naming aldehydes, it's always at the end, so we often leave off the 1. So this carbon will always be 1. Then we just name the alkane. So this is 3, so that'd be propane. We drop the E, and we add an AL, for short for aldehyde. So it's that simple. So this is propanal. Remember, stress the AL, not propanol. So propanal. And then we can add in prefixes just like we normally would. So let's try drawing a couple. So I'm going to name that one. Start by numbering your carbons. 1, 2, 3, 4, 5. That would be pentane. Drop the E, add an AL. So pentanal, it's got a methyl group at 2, a methyl group at 4. So 2, 4, dimethyl. And it's just like last one, run out of space. Dimethyl pentanal. Don't like that pen already. The problem with being at home, I can't throw my pens very far. My lab partner here would decide to chase them. So IUPAC's pretty easy, always end in AL. where we run into a little bit more trouble is the common names that we said in class. You have to memorize these. So just remember F, A, P, B, V. You'll have to, wow, this focus is terrible. You'll have to match these multiple choice. So formaldehyde, acetaldehyde, propionaldehyde, butyraldehyde, valeraldehyde. Remember, they all end in aldehyde. So memorize those. FAPBV, not too bad. We talked in class about the alpha, beta, gamma positions. So anytime you have your carbonyl, alpha is the first carbon over, beta is the second. So even when we do ketones, they'll have two alpha positions. So alpha is not the carbon in the carbonyl, it's the carbon next to the carbonyl. All right. So 1, 2, 3, 4. IUPAC name of this, butanal. Common name of this, FAPBV, 1, 2, 3, 4, butyraldehyde. So a little bit of memorization, but it's not too bad. Not too bad. So got to do that memorization for the IUPAC. The hardest part for that is keeping up with which one's which, IUPAC or common. So that's not too bad. Ketones, you're going to number it so that the carbonyl gets the lowest possible number. So I'm going to go right to left. 1, 2, 3, 4, 5, 6, 7, 8, 9. So we've got 9. So that would be nonane. It's at 3. And then I need to replace this E with ONE, as in ketone. ONE. And so that's pretty much it. This is 3 nonanone. That's always a fun one to say. Alright. Not too bad. Lowest possible number. Remember, I decide to go this numbering. 1, 2, 3. I'm going to go this way, get the longest continuous chain. So 1, 2, 3, 4, 5. This will be pentanone with a 3-methyl. But notice I could have had this ketone in multiple places, and so 3-methyl 2-pentanone. Now IUPAC tried to fix this. They tried to make it 3-methyl pentan 2-one, but nobody can read that. You just can't read it off when you're trying to give a presentation. So nobody uses that anymore. Let's see, so if I wanted to do this one, ketones, we don't have to worry about the common memorization, but instead the common uses a completely different system. It's much like our ether systems. And so here the parent group is ketone, and it includes the carbonyl. The side groups are down there, usually they're alphabetical, and so here I have a 1, 2, 3 propyl. I got a methyl propyl, one word, so methyl propyl. Here I have a methyl, alright, and then it's ketone. So 3 words. So any side groups just kind of get added on. This is an alpha methyl propyl, or you could have said a 1-methyl propyl. Those would both work. So common names are mostly used for easy things. So here I've got a 1, 2, and 1, 2, 3. So this would be ethyl space propyl space ketone. And the hard part here is this is 2 and 3. This is 1 carbon there. So even though I have a total 1, 2, 3, 4, 5, 6 carbons, when you just look at the first 2 words, a lot of times you forget that there's a 1 stuck in there. So if I was numbering this and doing this IUPAC, so this is common, and IUPAC is going to be 6 is hexanone, so hexane, drop the E, add an O-N-E, it's at 3, so this is 3 hexanone. So just keep up with which ones are common, which ones are IUPAC. So now we've got the idea of important aldehydes and ketones. So methanol, which is formaldehyde, gives us our embalming fluid. It's got a couple other preservative uses, but so methanol, 1 carbon, and so that one's pretty easy. Ethanol, it's what your alcohol, so if you have a heavy drinking, your body converts that over to ethanol, and you can actually, that's what you smell on someone's breath. So they've been out drinking, and then you say, oh, I can smell the alcohol on your breath the next morning. No, you're actually smelling this aldehyde. Aldehydes have much stronger smells than alcohols. Propanone, 2-propanone, we said is our organic solvent. That's our favorite. That's acetone. So making it aldehydes and ketones, the key to this is we're losing this H and this H, so we're oxidizing things. Potassium permanganate or chromic acid, that's that one that likes to eat through everything. And keep in mind, it's the carbon that's attached to the alcohol. So primary alcohols give us aldehydes, and then those go further on to carboxylic acids, so we have to be careful about those, and we'll actually use that later. Secondary alcohols will give us ketones. Remember, tertiary alcohols do not react at all, and so they won't be oxidized. So we did this in the alcohol chapter, and so this is now how we make these. Alright, so because we can go ahead further with aldehydes and take them on into carboxylic acids, we can use this as a test. And so instruments are really good at detecting carbonyls, but trying to decide whether you have an aldehyde or a ketone can be kind of tough. Their chemistry is very similar, and so trying to pick those apart, a lot of times we use just a simple oxidation test. So there's 2 that we like to talk about. The Tollen's test is our first one. Tollen's test uses silver. I'll let you read up on it. It's actually a really cool one. It actually makes a mirror inside a test tube and coats the inside of that test tube with for a positive test. So a negative test, you just get a solution, and then a positive test, the mirror, the test tube turns into a mirror. It's really nice. A Benedict's test, a little nastier looking, but much more useful. So when we take this, it'll react only with an aldehyde. Keep in mind, both of these rely on the fact that ketones do not further oxidize, and so when this copper reacts, it goes from copper +2, which is a nice beautiful blue, and then it makes copper +1, but that reacts with oxygen real quick, and it makes a kind of reddish powder. And so immediately the solution goes from blue to red. But what's also nice about it is it's proportional to the... Hey, welcome back. So, sorry about that. My lab partner decided that he wanted to taste test some of these. Aldehydes and ketones actually are found in a lot of flavorings, especially our artificial flavorings. Very distinctive smells. Really great lab. That's a hard one to do on video. How are we going to smell banana Laffy Taffy? But oh well. So went ahead, drew out some of our plans here for oxidations. So we want to keep in mind alcohols, primary alcohols go to aldehydes, which go to carboxylic acids. So our Tollen's test, our Benedict's test, they all rely on this last step. If I'm going to go all the way, we'll say oxidized completely. Always watch for that language. So primary alcohols, we said they'll oxidize twice. You lose the hydrogen. So make two, break two, we're losing our two hydrogens there, and that makes our aldehyde, and then we can add in our carboxylic acid. Secondary alcohols go to ketones. Tertiary alcohols don't have this hydrogen, and so they don't react. The next little part of this, then, we're going to reverse these reactions. We're going to go the other way. We're going to start with the aldehydes or the ketones and go back to the alcohols. And so to make them, we did oxidations where we were focused mostly on losing hydrogen. And so then we'll be gaining hydrogen to go the other way. So we've already talked in the past about ways to gain hydrogen. And the best one by far, we said we just take hydrogen and we needed a catalyst, palladium or platinum or nickel. And so that is a reduction. It was also our hydrogenation. So we'll use both of those terms now. And so when we do this, we can use not only the palladium, platinum, and nickel, but we also have NADH, and that's what your body uses. And so it's just a nice way of reducing it. And it's way too big. You'll notice down here I've got all this R groups. So those R groups, didn't want to have to draw the whole thing. Big, long, complicated. The important thing is this generates two hydrogens and two electrons. That helps reduce this. Remember, reduction is gaining electrons. So we're going to take our carbonyl, and add things across it. And so if we add two hydrogens, we'll be breaking two, making two. You can see that'll go to our alcohol. So primary alcohols from aldehydes, secondary alcohols from ketones. And then our new reaction here then is an acetal and a hemiacetal. And we did this in lab, and we said it was the result of coming in and lining up this polar alcohol group. Keep in mind, slightly positive, slightly negative, slightly negative, slightly positive. That's why it's going to line up this way. Always this way. See if we can even see this orange. And so I'm going to make these two, and I'm going to break these two. And we said we would get this form. and it has a very distinctive structure. So I'm going to put a little tick there so I can tell these two R's apart. It doesn't matter. This is an H. If we started with an aldehyde, if I started with a ketone, it would be whatever's there. But my key group here then is oxygen, carbon, oxygen, and so there's my functional group. I've got an ether link on the same carbon that has an OH, so this one is a hemiacetal. And we said that these are not very stable unless they're part of a ring, in particular 5, 6 membered rings. Those are stable. If it's not part of that ring, then hemiacetals go ahead and react again. We lose water. And so let's draw that out. We played a bunch with this in lab right as we were getting done. So starting off, and I'm going to take another one of my alcohols. There's the water that leaves, and then we connect this over. Oops, this should have had our OR coming off of it as well. Where did I mess up? It would have been here, and then you see the water has to leave when this gets made. So let's try redrawing that. Terrible. There's my hemiacetal. We had an H before. We have an H or an R. Now we line up my water. So my new alcohol comes in, and we're going to break two, make two. So I'll make these two and break these two. Hey, look at that, 4 bonds. Now I have carbon, oxygen, carbon, oxygen, carbon. Key bit being here, 2 ethers on the same carbon. So this is an acetal, much more stable. What am I going to mostly ask you for in class? I'm going to ask you about, is it a hemiacetal? Is it a hemiacetal, or is it an acetal? You're looking for the H for the hemiacetal. So I'm going to do all the fancy drawings here. You can follow along with that. Now, one of the key things about this is that we can turn around and make a ring structure, and so we can. That's the end of my being able to move my mouse properly. We make a ring structure, so it acts intramolecularly. That's the key. 5 and 6 membered rings. We'll see a lot of this when we start looking at sugars. They react intramolecularly. You can even react with 2 parts of it. And so in lab we also looked in at protecting groups, and we said that we could use instead of 1 alcohol, use a diol, and we could form a carbonyl with those 5 membered rings that are protected. And so this is a nice protecting group. Remember, aldehydes, ketones, that carbonyl is very reactive, as well as those alpha carbons, very reactive. So we want to protect them. That's how we do it. So we talked a little bit about enols back when we did our addition, hydration of alkynes. And so alkenes with an alcohol on them are called enols. They are not stable. They immediately go to a carbonyl, which is much more stable. And so that tautomerization, main thing on that is if you draw an enol, it's wrong. So just gotta keep in mind of that. And that will wrap up all of chapter 13. So the main thing we're going to focus on then, we've got common naming, IUPAC naming for aldehydes and ketones. We've got oxidations and reductions, although they're pretty straightforward. Just got to keep in mind make two, break two, and you got to figure out where that hydrogen's coming from. So, all right, we'll see you on the next one.